I'm talking to you. This is Goddess of Science Physics, and I'm Mrs. Bolden, and today we're going to talk about the Doppler effect in part 6 of my wave series. Okay, let's get into it. So as a wave source approaches, an observer encounters waves at a higher frequency more often. As the wave source moves away, the observer encounters waves at a lower frequency. Okay, this is probably the most difficult concept in this chapter, but we can do this because we can do difficult things. All right, it's not that difficult. All right, so we're going to start talking about a bug that's wiggling its legs. It's sitting in a puddle, and it's bobbing up and down right here in the middle. And by wiggling its legs, it's a source of vibration. So it's creating waves that move out in all directions because it's sitting still. So if you were at A in the lake or the puddle, you would see the frequency of the waves would be exactly the same as if you were sitting in B. Okay. So the wave crests make concentric circles, which is one inside the other, because the wave speed is equal in all directions. Okay, that's pretty logical. You can probably get your mind wrapped around that. So the bug bobs in the water at a constant frequency, so it's moving its legs at a constant rate. The wavelength will be the same for all the waves. So he's like kind of working it out there, moving his legs all at exactly the same rate. So the wavelengths and the frequencies are going to be exactly the same. Excuse me. So if you were standing over here in A, the frequency of the waves getting to you would be exactly the same as the frequency the bug is making the waves, the frequency of the bug. Excuse me, I have to take a little drink here. There we go. Okay. So now, if the jiggling bug isn't sitting still, but he's moving across the water at a speed that's less than the wave speed, excuse me, the wave pattern is no longer concentric. The center of each crest is made when the bug is at the center of the circle, but the center of the next crest is made when the bug was at the center of that circle, and so on. And I have a little picture here. So what's happening here is he's jiggling exactly at the same rate, but instead of staying in one place like when he was over here, now he's moving along, and the wave starts from him. But because he's moving toward B, the waves are going to reach him more. If you were standing at B, the waves would reach you more frequently than if you were standing at A. Okay. So, and you're like, what does this have to do with the Doppler effect? Well, this is the Doppler effect. So, the bug has exactly the same frequency as it had before, if it was sitting still, except this time it's moving toward position B, if you were standing at B. The observer encounters a higher frequency at B because the bug is moving toward him. If you were standing at A, the frequency would be less than the frequency that the bug is making the waves because the bug is moving away from you. So each successive crest has a shorter distance to travel, so they arrive more frequently in the B position. So in this short amount of distance, you're going to get 1, 2, 3, 4 waves. It's not going to take very long before those 4 waves pass the B position. However, the A position is going to see the waves at a much greater, going to be longer in between waves. So the bug is moving away from the observer with a lower frequency of F. So if you were A, the frequency is going to be much less. The waves won't come as often. There's a longer time between the wave crest arrivals, which kind of makes sense if you look at the picture. They're coming very frequently if the bug is moving toward you, comes less frequently if the bug is moving away from you. So each crest has to travel farther than the one ahead of it due to the bug's motion, because the bug is moving away. This crest has to travel further than this crest, and so forth and so on. The Doppler effect is the apparent change in the frequency due to the motion of the source or the receiver or both. All right, now notice it says the word apparent. It isn't an actual change in the frequency that the waves are generated. It just appears to be a change in the frequency because the thing that's making the wave is either moving away from you or moving toward you. Works the same way if you're moving toward toward the source of the wave, or if you're moving away from the source of the wave. The greater the speed of the source, the greater the Doppler effect is going to occur. All right, so this is a little crazy. It is very abstract, but you all have actually experienced this. If you've ever stood on a street corner and had a fire truck with its siren on come toward you and then move away. As the fire truck gets towards you, the frequency, it gets, higher and higher, and then as it moves away, it gets lower and lower. So the Doppler effect causes a change in pitch of a siren. So the fire truck approaches, the pitch sounds higher than normal, the sound wave crests arrive more frequently. Is the fire truck actually producing a higher pitch sound? No, it's exactly the same pitch sound as if it was sitting in front of you and making that noise. It's just because it's moving toward you that it sounds like it's a higher pitch. So notice here's the fire truck, all right? And notice how squeezed together the waves are, so it appears very high pitched. However, when it moves away, it appears to have a lower pitch because the waves don't reach you as frequently. So when the fire truck passes and moves away, you hear a drop in pitch. The wave crests are arriving less frequently. So you get a kind of thing going on there. Okay, so police use the Doppler effect of radar waves to measure the speeds of cars on the highway. So that's kind of how their radar detectors work. The radar waves are electromagnetic waves, and this kind of gets into our next bit, which is our next chapter is on sound, and then after that we have other electromagnetic waves. Police bounce them off moving cars. A computer built into the radar system compares the frequency of the radar with the frequency of the reflected waves coming to find the speed of the car. So that's how radar detectors work. So here's the police with his radar detector here, and apparently it's a police car from the 1950s. And here's the person sends the radar waves out, they bounce back, and then how frequently they reach the receiver here tells the police how fast the car is going. Okay, that's it for this time. Thanks for joining me. Have a great day.